Hi everyone, welcome to lesson 2 of our radicals units. Today's lesson is all about the square root of a function. But before we start there, we're going to start with our opening question here. Just as a quick refresher, we're going to talk about mapping. So the very first thing for this question here to figure out our mapping notation for a and b is to simply rewrite this equation. We want to isolate this y variable and we want to get everything all to the other side and set up our equation. So here we go. So I'm going to move this 8 to the other side. That's going to be my first step there. So I have y equals negative radical symbol. That 8 is going to be at the end of this radical. But this radical here, I need to do one extra step. I need to factor out a negative 4 because I need a b value by itself. So I have a negative 4 right there. I have x right here. So negative 4 times x gets me back to negative 4. And I got to figure out what negative 4 times something to get me back to 2 here. Well, that something has to be a negative 1/2. In a close bracket, extend that radical symbol, and then we have our plus 8 right at the end. So here we have the following. We have a reflection. And this first one here is on our x-axis. We have a second reflection right here. That's going to be on our y-axis, so reflection. We have that 4 inside the radical symbol, meaning that that's a horizontal stretch. And that's going to be by a factor of 1/4. We have this negative 1/2, which is of course our horizontal translation. And that's 1/2 to the right, 1/2 units. And finally, we have this plus 8 here. That's our vertical translation. We're going 8 units up. There we go. We have our equation broken down. So what we want to do is rewrite our mapping. And here we go. So we have original x comma y is going to become. So we want to group together all things horizontal. So horizontal stretch, horizontal translation, and our reflection on our y-axis. That's a horizontal reflection, by the way. So we have our 1/4 x, that's my horizontal stretch. We have the negative there to account for the reflection, and we're going to add on our 1/2, comma, on the other side here for y, we have our negative. We don't have any stretches here, so it's just going to be negative y, and we're going to go plus 8 units, and there we go. We have our mapping completed. Don't forget to close brackets there. Going right into our questions here, example 1. So basically in example 1 here, we're just comparing two graphs. We have our standard y equals f of x, which is a straight line, and our second graph, which is just going to be the square root of f of x. And my square root symbol is missing around this equation here, so square root. And f of x was 3x plus 6, so it's going to be square root of 3x plus 6 here. And so I'm going to compare these two functions. The first thing I always compare is always, of course, the domain and range of each function. So for the domain, let's start off with our standard equation. So we got y equals 3x plus 6. My domain here, because it's a straight line, we're going, and I'm going to write this one in set notation, x such that x is an element of a real. Because we're going to negative infinity and positive infinity for our domain. For our range, the lowest we're going to go is negative infinity, the highest we're going to go is positive infinity. So here we have y is an element of a real. In my new function here, let's do it in a different color. So it's basically y equals square root of this 3x plus 6. What's going to be my new domain and range? And again, we have a picture here that we can definitely use to figure out our domain and range. So the furthest left we're going for our domain looks to be at -2. The furthest right is positive infinity. So we can set up our domain here as x such that x has to be greater than -2 but less than infinity. So basically x just has to be greater than or equal to -2, and we have x as an element of a real right after that. Our range in this case here, the lowest we're going to go is at 0, the highest we're going to go all the way up to positive infinity. So we have our range of y such that our lowest is 0, y, and y is an element of real after that first condition. Off to the side here, we have a little t-chart. That t-chart is going to help us figure out our coordinates. So we're going to rewrite a few of these. So I'm just going to slightly move this over just so that we can fit in our coordinates here. There we go. So let's take a look at a few coordinates just to compare what's happening. So the very first coordinate I'm going to pick is at -2 because both graphs share that coordinate. So I'm going to pick x equals -2. Another coordinate that I'm going to try to pick is, and let's take a look at our graph here, something nice. Let's choose something like x equals 3. We can choose that crosshair there. Or sorry, that's y equals 3, so that's at -1. Let's choose 0 and let's go with +1. Okay, so on our original graph, which is this line here, when x equals 2, y should be at 0. When x equals -1, y was at 3. When x was at 0, y should have been at 6. And of course, when x equals 1, y here should have been at 9. So these here are all my coordinates. If I had x values here, these are all my y values of the original. If I had to square root everything, none of my x value changes. It's just I have to square root all my y values. So if I square root 0, it's still going to be 0. If I square root 3, it's a radical 3, and you can't simplify that any further, so I leave it alone. Square root of 6 is just root 6, and again, that's also one that I can't simplify, so I'm going to leave that alone. And square root of 9, of course, is going to get me 3. And let's double check that at +1. Were we at 3? Yes, we have a coordinate right there. And there we go. I just dotted in the coordinate. After this, we have a part B. Part B is asking us to state invariant points. And again, reminder, invariant points, what are they? They are points that are the exact same on both graphs. So if I notice points that are the same on both graphs, at -2 for x, I have y of 0, and -2 for x, I have a y of 0 on both graphs. So that's definitely one of my invariant points at -2, 0. My other invariant point is going to be a bit tougher to find, but if we take a look at our graph, let's take a look. So again, I'm just going to highlight my invariant point just so that we see it. So again, at -2, 0, we have an invariant point right here. And I'm going to try to do that in a different color here. At -2, 0, we have an invariant point here. And the only other dot that we're crossing at that's going to be the same is right here. This coordinate here, I have no idea what x is, and so I want to figure out what x is here, but I know this y value right here though. My y value is going to be at +1. So what I want to do is to find this other one, I want to look at when y equals 1. So we have one invariant point at -2, 0. The other point is going to be, let's call it at x comma +1, because that's my other invariant point. To figure out this invariant point, we're going to substitute it into one of the two equations. Well, I would opt to sub into the equation that there's no radical symbol. So I would use the original y equals 3x plus 6. I'm going to sub in all my variables here. So we know y is 1. That's going to be equal to 3x, and that's what we want to solve for. Plus 6. Well, that's an equal sign, by the way. To isolate for our equation, we have here is going to be -5 equals 3x, and of course x is going to be equal to -5 divided by 3. So our second invariant point is now going to be, therefore, we have our second invariant point at -5/3 comma 1. So here we have two invariant points, and again, if you take a look at our graph, it definitely lines up that we have two invariant points. And again, just to highlight it, it was this dot right here at -2 and 0, and this dot right here, which we had to figure out our x value, and our x value is -5/3 and +1. And we knew that it was crossing at +1 there. In example 2 here, again, there's a quick note about invariant points. In the previous page before we move on, sorry, I'm going to go back. Just a quick note here, invariant points, so we found these two here, but all invariant points on all of these graphs will always end up at being at y equals 0 and at y equals 1. So we're always going to look for invariant points. I'm going to write that as a side note here. Invariant points at, sorry, that's an at symbol, at y equals 0 and y equals 1. And so for radicals, we're always going to look at these coordinates here at when y equals 0, y equals 1 for our invariant points. Going after this one here, so again, we're going to sketch a graph and then we're going to square root that graph. So I'm going to quickly pause this video so that I can sketch a graph. Sorry about that, folks, I was on the wrong question. So in example 2 here, let's start again. In example 2, so we have a graph given this time, graph of f of x given to us, it's a straight line, and we want to graph y equals f of x. So the way that we graph this line here is we're going to figure out some invariant points, put coordinates down on invariant points, and of course we want to graph all things where there's a y value greater than 0, because of course you can't square root anything below 0. So here we go. I'm going to start off with some coordinates. There looks to be an x-intercept right here at 3, 0. I'm going to put a coordinate dot there. The next one I'm going to put a dot at is when y equals 1. We definitely want that dot there when y equals 1. And then now I'm going to kind of pick and choose a few answers to put a coordinate on. I don't want to use 3 here because I don't know what the square root of 3 is, but I do know that the square root of 4 should be at 2. I'm going to look for not 5, 6, 7, 8, but I'm going to look for 9 somewhere because I know the square root of 9. 9 is right around here on the original graph. Square root of 9 should be 3. So I'm just going to go straight down to 3, and right here, that's going to be our other coordinate. So here again, how we did this is our y equals f of x line, and we are square rooting f of x. And remember, another way to say f of x is you're square rooting your y value. Here are all our y values, and you can only square root any y value greater than 0. Down here, to the right of this here, our graph kind of goes below the x-axis there, so we're into negative y values. We can't use that because you cannot square root a negative value here. So I'm going to try my best to connect these dots, and then I'll be right back. Alright, and there we have it. There's my graph. I've connected all my dots on here. Of course, I'm still missing an arrowhead at the end of here because this graph is going to go on forever in our negative direction here. We're not going to go any further on the right. So this is going to be my graph for y equals square root of our f of x. So from here, we want to answer a few questions right below. It's asking you to state the domain and range for each function and to figure out a few coordinates on our table of values here, then state any invariant points that you may have. So for our straight line, our y equals f of x, for a straight line y equals f of x, we have our domain and range. And in this case, for domain and range, we've been doing set notation, so I'm going to switch over to interval notation for this one here. So for our domain, we're going from negative infinity to positive infinity. So we have negative infinity, positive infinity. There we go. That's our domain. And for our range, the lowest we're going to go is negative infinity. The highest we're going to go is positive infinity. And there you have it. You have our domain and range on the original. On our new graph here, which is y equals square root of f of x, So again, this is our new function, and you're square rooting all the y values from the original. So our domain is going from negative infinity all the way up to positive 3. And we want to include 3 because there was a coordinate there. Our range, as low as we can go, was 0. And the highest we can go was positive infinity there. And there you go. We have our domain and range for our old and our new, or our original and our image graph. Let's state some invariant points and then we'll fill in this table of values there. So invariant points. So my invariant points are going to be when y equals 0 and when y equals 1. I have two coordinates here. My two invariant points are going to be our x-intercept here at 3, 0 and this coordinate here at 2, 1. So stating the invariant points, we'd have two of them. We'd have our x-intercept again at 3, 0 and our other invariant point at 2, 1. And again, for our radical graphs, we're always look at y equals 0 and 1. Those are where our two invariant points, or our invariant points for radicals, should be lying. Switching over to our table of values here, so I'm going to cheat a little just because I already picked a few coordinates. So I'm going to pick about 4 of them, and they're all going to line up on both graphs. So again, my coordinates that I'm going to pick here are going to be, let's pick x equals, let's do 3, let's do 2, let's do -1, and let's do -6. At x equals 3 on our original graph, we should have a y value of 0. At x equals 2, we should have had a y value of equal to +1. -1, you should have been at +4. And at -6, you should have been at a value of +9. So again, if you were square rooting your y values, so again, here, if you subbed in x into this equation, you got your y values, and here it's saying square root all of these y values here. Our new coordinates would have been square root of 0 is 0, square root of 1 is still at 1, square root of 4 is now at 2, and of course square root of 9 will be at 3. And these are coordinates that I just kind of picked earlier, and it helped us graph out my radical function here. In the next example, I'm going to ask you to draw both graphs here. So in this case here, I want you to draw the original y equals x squared minus 9, so that's going to be a parabola opening up, starting with a vertex value at 0, -9. So you want a vertex opening up. You want to sketch that one first and sketch as many dots as possible on that first one, and then we'll talk about the radical function. So I'm going to quickly sketch out my first graph here. Okay, let's talk you through some of the coordinates that I chose to graph my y equals x squared minus 9. So, of course, I'm going to have my vertex here. My vertex was at 0, -9. My next coordinate was at 1, -8, and respectively, -1, -8, because they had to mirror. The ones after that was at 2 and -5, and of course, -2, -5. 3, 0, -3, 0, and finally 4 and +7 and -4, +7. Of course, they have to mirror to be our x squared, our parabola graph. From here, what I want to do is square root all my y values and then see what my new parabola is going to look like. So again, if you had to square root all your y values, again, you can't square root any of these negative y values down here. You'd have to start on your x-axis going up. So for this one here, this section of the line here, that's a positive section. It's above our y, or above our x-axis. So here, I'm going to put a coordinate right at that y, or at that x-intercept. I'm going to put a coordinate right here as well. Okay. Coordinate here as well. The reason why there's a coordinate here is when y equals 1, I know there should be a coordinate there because that's going to be my invariant point. And same thing over here. I have invariant point on my y equals 0 and when y equals 1, which should be somewhere approximately there. After this, it gets a bit tougher to figure out where your next coordinates are, but with these two here, it's kind of tough to do. So I'm going to go and switch over to my graphing calculator and then try to find a few coordinates there. So here I just loaded up my graphing calculator. I made sure that everything was nice and clear and out of the way. So the first graph, of course, I'm going to graph is x squared minus 9. And the next one I'm going to do is the square root of x squared minus 9. And again, before I hit graph here, just double checking what I already have. I have a parabola going up, and I have two invariant points here, two invariant points over here, and I want to figure out, well, where are some of my other coordinates going off to the x positive and to the x negative direction. So once I hit graph, I'm going to look for something similar. There we go, there's my parabola, and I have my two radical pieces, one in each direction going off to the positive and to the negative side. Here I'm going to try my best second graph to figure out if I can pull off any other coordinates. And it doesn't look like we have anything really nice here. We got 3, 0, we have 5, 4, and I bet you at negative 5, we'll have a 4 there. So I'm going to use that coordinate as well. 5, we're at 4. And I have about three dots here, and it's going to be good enough to build my graph. So there we go. Just connect my dots now. There we go. Arrowhead on the end of it, because these are going off to infinity, or they're going to continue at least. So there we go. We have my graph all done, and on the bottom of this page, we just have to fill out a few characteristics based off of the original versus the new. So let's talk about our original x-intercepts. And again, for x-intercepts here, I want to write down some coordinates. It's never good enough to write just x equals, but let's write down our coordinates. So we have x-intercept of 3, 0, and at negative 3, 0. We had a y-intercept, and that so happened to be at 0, negative 9, aka our vertex. My domain is, and let's write this in set notation, but I'm just going to skip a few steps here. So I'm going to just do the curly bracket, and this is the improper step, our set notation. So x is an element of a real. So there we go, set notation range. The lowest we went was negative 9, the highest is off to infinity. So we have negative 9. Y had to be greater than negative 9, and of course y is an element of a real after that. Invariant points we'll deal with on the bottom here. Let's switch gears. Let's talk about our radical graph. So our radical graph is broken up into two pieces. Let's double check. Do we have any x-intercepts on them? Yes, we do. So I'm going to jot down my x-intercepts. Of course, I have negative 3, 0, and 3, 0. Here, do we have any y-intercepts? No, we don't. Neither of our red radical graphs are touching or even close remotely to our y-axis there, so we don't have any y-intercepts. So it's never good enough to leave this as blank. You need to write something in. Don't write 0, because 0 means that you have a y-intercept of 0. Here, I would literally write in the word none or no y-intercepts or none, something there in text format. Our domain, let's talk about our domain. So again, we have two graphs, so let's start writing down both graphs. So we have this one here on the far right. So the one here on the far right starting at 3 going off to infinity there. So we'd have one domain at our lowest value would be at positive 3, and x had to be greater than or equal to positive 3 going off to infinity. So x is an element of real there. And the other one, if you take a look at it, was at negative 3 going off to infinity, negative infinity, in fact. So here we would have our other domain of negative 3 So we want x to be less than or equal to, sorry, and my writing is not coming up right now. We want x to be less than or equal to -3 for our other domain. And x is an element of a real still here. For our range for both of them, the range is going to be the same on both. They're both starting at 0, going off to positive infinity for both. So I can just quickly jot down just one range there that would do it for both. So you'd have 0, y there. So y has to be greater than or equal to 0, and then y is an element of a real. Invariant points, this is the last part of our graph here. Invariant points, where are they? They're going to be the exact same on both. That's why they're invariant points. So the first one, of course, we have our x-intercepts. So we have invariant point at -3, 0, and at 3, 0. So that first takes care of one case for invariant points, the case of y equals 0. Now we got to figure out the case of when y equals 1. So when y equals 1, I'm going to sub it into that first equation, which is y equals x squared minus 9. And instead of saying y, this time I'm going to say 1 because I do want a y value of 1. Isolate for x here. So I'm going to move this over to the other side. So we'd have 10 equals x squared. And of course, I'm going to square root both sides. So x is now going to be equal to plus minus root 10. And again, why do we have plus minus? Well, if you had to square root a variable, and x so happens to be a variable, by the way, whenever you square root a variable, you always have a plus minus symbol as well attached to it because you don't know if it's the positive or a negative variable. So here, if you have plus minus 10, that means we have an invariant point of root 10, comma 1, and negative root 10, comma 1. So we'd have these two as well for invariant points. So right now, how many invariant points do we have? We have 1, 2, 3, 4. In example 4 here, again, it's similar to example 3. We're going to sketch out our graph, and then we're going to sketch out our radical function right on top of it. So I'm going to quickly pause it to sketch our graph out. Here we go, folks. So I did do a quick sketch of negative x squared plus 4. So that means our vertex would have been at positive 4, negative meaning that we would have had a reflection over our x-axis, so it should have been a parabola going down. I sketched out about 1, 2, 3, 4, 5, 6, 7 coordinates here as best as I could, and that's going to be my parabola. In the next part of this question here, we're going to square root all of our y values again. Again, in this question here, we do not want to square root anything in the negatives for y. We just want to square root all the positive y values. Well, here we have 0, so we're not really square rooting that. So I'm going to double up on these coordinates here. At 1, we know we have an invariant point right here. And at 1 over here. And sorry, that's slightly off. And then the tougher ones to do is what's the square root of 3? And you'd be more or less guessing where the square root of 3 is, which is about 1.7. That's going to be right there. And here we have a y value of 4, and of course the square root of 4 should be right at 2. And so if I connect all my dots here, I should have a smaller dome right underneath our parabola. And there we go. Once we have this done, we're just going to go and again, of course, fill in some of these characteristics. So on the original, what are my x-intercepts? I had 2 of them. They were at -2, 0, and at +2, 0. We had a y-intercept, and that was at 0, 4. 0, +4. Our domain here, and let's do this, I believe last time we did it in set, so we're going to do this one in interval notation. Our domain here is from -infinity to +infinity. Our range, the lowest we were going was -infinity, the highest we could go was +4, and we wanted to include +4. The domain and all range and x and y intercepts of our new function, let's go. So again, we have the same x-intercepts. So we'd have -2, 0, and +2, 0. Our y-intercept is slightly different here. Our y-intercept is going to be at 0, 2. Our domain here, we're stuck, and if you take a look at our graph here, our red section is only this little section here, so we're stuck for our domain. Our domain has to be between -2 and +2. We're stuck in between those values there. And my range, and again, it's our little red graph here, so our range, the lowest was 0, the highest we went to is 2, so our range is very, very limited here. So our range is going to be from 0 to +2. Our invariant points, let's finish off this question here. Our invariant points, we're going to have a few of them. So the first set of invariant points, of course, are going to be our x-intercept, so we'd have -2, 0, and at +2, 0. After that, we got to figure out when y equals 1. So again, I'm going to sub in my value of 1 equals, and our original was -x squared plus 4. Here I'm going to isolate for x here. So I'm going to move this 4 to the other side. So now you'd have -3 equals -x squared. Getting rid of the negative on both sides. So that's 3 equals x squared. And of course, square rooting now, you'd have x equals plus minus √3. So therefore, you'd have another invariant point at √3, comma 1, and at -√3, comma 1. So again, you have about 4 invariant points on this question here. Our last question for the day, state the domain and range of y equals square root f of x if f of x equals x squared plus 7. So for this one here, let's do a quick graph, and I'm going to use my graphing calculator to help me figure out my domain and range. So here our original graph was x squared plus 7. And my new function was the square root of x squared plus 7. And I'm going to hit graph because I'm ready. Let's see what a graph looks like. And there we go. So we have the original right here in blue and the new one here in red, and I'll copy that into our notes just so that we have a copy. And again, of course, this question here, I didn't ask you to graph by any means, but I did want to write down the domain and range of the new function. So the domain of the new function, and let's do, yeah, it's okay. Domain of the new one, we're going off to -infinity, +infinity. It's this red graph here. So it's going to be everything. So we got -infinity to +infinity. Our new range will be right down here, this lowest value here. This lowest value here, of course, has to be the square root of 7. And we're going off to +infinity there. So we got the lowest value of √7 going off to +infinity. And there we go. We have stated domain and range for this graph here of the new function. Again, if you have any questions, please feel free to ask. We'll see you in class.